Thanks. So let me just quickly summarize where we were. Sorry, is this was the place? No, this line is how far I should go? Okay. Yeah. Okay. So so we started with talking about topology of D equals 0 systems. And the important thing was we came up with a topological invariant, which were basically things that didn't change with continuous change of Hamiltonian. Okay? And depending on symmetry class, so we had then a bunch of symmetries. And out of the symmetries, there were time reversal, particle hole, and let's say chiral symmetry. And then there's also no symmetry, let me call that A. And in this case, in the no symmetry case in 0 dimensions, we had a Z invariant. With time reversal, we had 2Z. With chiral, we had nothing. With particle hole, we had ZJ. Right? And this basically just had to do with looking at the degeneracies of the eigenvalues from symmetry and how the spectrum changed when you changed parameters. When did an eigenvalue cross 0? Or what happens when an eigenvalue crosses 0, just from looking at that. That was part 1. And then for D equals 1, we started looking at a Majorana chain. And there were two things that we concluded. One was that, so this had particle hole symmetry. And there was a zero energy mode. Energy isolated Majorana N mode. In a so-called topological phase. Okay? So this gave an example for a topological edge mode. And so we had I would say actually, let me call it bulk here. Bulk. There was a topological bulk invariant looking from 0 dimensions. And then looking at 1 dimension, we came up with these topological edge modes which cannot go away, which required, if you remember from this plot here, this was our picture of the topological edge mode. There's an isolated Majorana mode at the end. But the isolated Majorana mode at the end is a feature that cannot happen in an isolated system. Any real system has to have an even number of Majorana modes. And finally, if you looked at this kind of plot, what we found was that you needed to change your Hamiltonian by a finite amount before this mode could go away. This was the other, this is why it was topological. All right? So okay. And the other key thing was that this mode was protected by particle hole symmetry. Because the basic idea was that if you had an isolated 0 mode, like here, if a continuous deformation has to move it away from 0, then you can, as soon as it moves away from 0, you ask, okay, what is the particle hole? The states have to come in pairs of E and minus E. So what is the minus E partner of this, it can't be there, and therefore this just can't move away from zero. That was the argument. Okay? So, okay. So any questions about that part so far from last class? Yes. Yes, exactly. That's a good point. So that did not have directly to do with the eigenvalues, but you had to look at the Fermi unparity to understand why it was. Okay, very good. So now so the next thing that we're going to talk about is connecting these two. So basically, but before we do that, we need to understand the bulk of the D equals 1 Majorana, the one-dimensional Majorana chain. That's the next step, right? So we need to understand the bulk spectrum of the Majorana chain, and for that, basically, we need to go to momentum space. So what going to momentum space means is that, so if you remember, we had some kind of a lattice Hamiltonian. It's a one-dimensional chain labeled by with each site being labeled by state n, and then we just form. But because we have translational symmetry, so now you should think of not an open chain, but a chain with periodic boundary conditions. So it connects at the ends. So you have translational symmetry, and because if you have translational symmetry, momentum is a good quantum number. So K is a good quantum number, and you can use Bloch's theorem. I'm hoping everyone's good with Bloch's theorem. To write the superpositions, and when you do, so what you can do is now let me just scroll back a little for a second. So we had a Bogolubov. Where's the Bogolubov? So yes, so this was our Bogolubov-Dijon Hamiltonian. All right. One thing, right? So n represents the sites, and tau represents the particle and hole index on each site. Remember, there was a spinner on each site, Cn dagger. So this goes to, you can write it as, it becomes when you go from second quantization to first quantization, this becomes a spinner, and these so-called Nambu matrices are Pauli matrices tau x, tau y, and tau z that act on this two-component space. Right? Yeah, that's right. So this was really a set of CNs. But actually, so sorry. Let me actually no. Let me look at the spinner on each site instead. So it's Cn. So before we had the whole C, and I'm just looking at the C on each site. And I had a particle and hole operator for each, so I have a chain, like the one we were drawing before. These are, so to correspond to the figures we had before, these are fermions, C dagger 1, C dagger 2, and each one of them has two Majorana fermions. Right? Gamma 1, right, and so on and so forth. Right? Excuse me. And but you also have the hole on each of these sites, and together I'm calling these capital C1, capital C2, and so on. This is just notation, okay? And when I go to, so this is second quantization, and when I go to the matrix, when I write down the matrix corresponding to this is like the Bogolubov-Dijon matrix. So then what happens is I have sort of a tensor product representation. I have sites, so this is site 1, but it has a particle hole. There are two degrees of freedom per each site. Right? So it's 1, and then 2, so on. So the Hamiltonian, so you should think of this as sort of some kind of spin. You should think of this as some kind of effective spin I have. If you're, I mean, mathematically, it's just like a spin. And all that means is that when I write the Hamiltonian, I have something like looks like this. I mean, let's say I have a chemical potential term, which is diagonal in sites. It acts on each site. It does not change site. But there is a for spin up, it is something, and for particles, it is positive, and for negative holes, it is negative. Yeah, absolutely. It's a term that came from mu c dagger c minus cc dagger, but I don't want you to always read it that way because, I mean, ultimately to calculate, going back to the cc dagger notation is quite useless. I mean, this is just a regular, what you'd call a tight binding model. And the only difference is that there are some, so it's a tight binding model for a particle with spin. So you have, so this represents, let's say, yeah, what I said, it's an on-site term in the tight binding model with, actually, does the word tight binding model make sense to everyone, or would someone like some clarification on it? Okay, all right. And this term represents going from site n plus 1 to site n, and so on and so forth. But you would have this combination of spin. Yes. This n? No. So this ket n. That's a good point. If there are capital N sites, let me call it capital L sites. If it's L sites long, then there are L components. Yeah, but. Okay, but you should remember it's a tensor product. So right, so the total basis. So this is L dimensional. So it goes from 1, 2, 3, 4 up to L. But then it's multiplied by 2. Right? So it's ultimately the whole Hilbert space is 2 L dimensional. Everyone happy? Okay. So question? Okay. Okay. So we have this Bogoliubov-Dijon Hamiltonian. Now the next thing we have to do, so now we have to calculate, understand its spectrum with periodic boundary conditions. So let's see. So you use Bloch's theorem, and you make this substitution, this change of basis. And when you make this change of basis, you calculate the Hamiltonian. So the magic of the symmetry is that the Hamiltonian turns out to be diagonal in this basis, almost. So you just get some Hamiltonian that looks like this. 2k, 2t cos chi. So basically this whole L dimension is gone, and you just have basically a 2 by 2 matrix. Right? And the Bogoliubov-Dijon Hamiltonian you can now think of as a sort of a tensor product in this nice 2 by 2 matrix. But the nice thing is now, so the advantage is before you had to diagonalize a 12 by 12 matrix, but now you can just diagonalize a 2 by 2 matrix, and we'll understand the bulk spectrum. Okay. So this is, again, a standard trick, not really, nothing much to do with topology. But now we have to understand what does particle-hole symmetry do in this block space? That's the next step, right, to understanding this. And so if you work through the application of the particle-hole operator, because it is anti-linear, it changes k to minus k. And because it changes k to minus k, the constraint that we had before finally becomes like, okay, I apply particle-hole to my Bogoliubov-Dijon Hamiltonian that I did before. K changes to minus k. I do a change of variables. And finally, I conclude that this is the condition on the particle-hole operator. Because the particle-hole operator, we argued, had to change the sign of the Bogoliubov-Dijon Hamiltonian. So this is a few quick steps that we did. But the basic idea is that, so we transformed our Hamiltonian to momentum space because it's now block diagonal. Momentum is a good quantum number. But we have to now ask, how does the symmetry act in this transformed basis? And this is, again, you can read through this algebra later at your leisure, but the important thing is this, that h at k becomes minus tau x h star minus k. And k goes to minus k under particle hole transformation. Okay? So, and you can actually, so this was a general argument, you can actually take the h of k that we calculated and actually explicitly check that this is actually satisfied. So the important thing is that not each k by itself is particle hole symmetric. It's only k's that are special, which such that they turn to themselves, which are k equals 0 and k equals pi. Only those two are symmetric under particle hole symmetry by itself. So that's what we have to keep in mind when we're so we have to focus on these special points, k equals 0 and k equals pi, to understand the topology of the system. Okay. So, and again, but the idea is that once we have gone to momentum space and we have moved to these special k points, we have gotten rid of our one dimension. Our d equals 1 problem is now has turned back into the d equals 0 problem. And if we understand the topology, since we understand, and we can use the fact that we understand the topology of d equals 0, talk about d equals 1, and we have to just look at eigenvalue and gap closing. So let's just look at the band structure first of E of k. So h of k, we had a band structure. So we can calculate the spectrum of h of k analytically, and it has just this simple form. Again, this is, I'll just leave you with a little bit of algebra to do. And you can just plot the spectrum here. So, okay, so this is our E versus K for different mu's. So you remember before we had this, so what we're plotting as a function of mu, because we had this plot before of the 0 modes where we saw that the Majorana modes existed in some range of mu and then went away for higher range of mu. So let's see what happens to the band structure when we change the mu. So again, you see that the band structure, the gap closes as we drag the mu. It closes completely. So at this point, this is the similar gap closing phase transition that we had before in d equals 0. It's like now you have eigenvalues crossing 0. And at this point, when you go higher, now you have completely gone back to the sort of trivial phase. Okay, at least there's a possibility that one side of the transition is topological, the other side is trivial. So at the least you could guess from here. So what you can do, and the gap closing happened at k equals 0. So what you can do is just look at this spectrum at k equals 0. This is an analytic form. You can look at it at k equals 0, and what you would get is, so let's say d equals 1, and topological bulk invariant. But I want to set, so if I set, so E of k is this plus or minus square root 2t cosine k minus mu square plus delta squared sine squared k. This is the dispersion of the Kitaev chain. If I set k equals 0, then this just becomes plus or minus mod 2t minus mu. And so all we need, so the transition, so the for the Majorana chain, let me get rid of the transition point is at 2t equals mu. That's one of the transition points. Right? So that critical point beyond which there was no Majorana, that could be around there. That's the potential place. So, any questions so far? We don't have Majoranas? No, that's a good point. So I didn't actually give you. Okay, okay. So let me. So I haven't given you a complete argument for that, but let me. So but based on what I've told you so far, what you can infer is that the Majorana cannot move unless the bulk gap closes, because you need the two Majorana. So the isolated Majorana cannot move. They can only move if they talks to the other Majorana, because they have to move in pairs. Particle symmetry forbids single Majoranas from moving. So if you remember, as we got to the transition, the wave functions started to talk to each other, which means that it was easier for the wave functions to move through the bulk, which is saying that the bulk gap is closed. And because I'm not completely giving you the entire, I'm giving you a hand wave here. The more precise statement is, so then this is a general statement for states in a bulk, and okay, I'm not going to derive it in detail. But so the statement is that if you have a state, any bound state in an insulator, in a gap system, the decay length for that system, for a wave function of that bound state, is inversely related to the gap of the system. So you might be familiar for the coherence length in a superconductor. It goes as velocity divided by the gap. So as the gap goes to zero, the coherence length. So it's the same thing. The Majorana decay length increases, and right? But that's kind of a subtle. Okay. Yes. Yes. No, that's the great point that I'm coming to. I haven't told you really which part is topological and which part. I just told you that the boundary would be t equals 2t equals mu. But which side is topological, which side is trivial, I haven't told you. And ultimately, I'm going to jump in and I'm going to show that it's related to that same Pfaffian that we did with d equals 0. So it's going to be the same. Okay. So now I guess this is another general principle, so I guess I should explain this. So what we did, in the past things, what we did was we studied sort of how a specific model, right? This Kitaev lattice model. Whenever it was nice, you can just solve it completely, and you don't have to, and you can get we could get a lot of things. And actually, just as a general reference, Kitaev, he is this certified genius because he won the MacArthur Award, he won the Breakthrough Prize, and he's sort of one of the most, I would say he has been one of the most recent creative and influential condensed matter theorists, because he came up with three distinct models. One is this Majorana model, the other is the toric code model, which explains Z2 gauge theories, and the third is the honeycomb model, I think, which you're going to hear about, which is a fascinating marriage between Majoranas and Z2 gauge theories. The beautiful thing about all these models is that they represent physics that is actually relatively esoteric field theory of gauge fields, but in a model which literally, like in any undergraduate, can start solving. Right? So that's what's so fascinating. So that's good. But at this point, what we want to do is argue how to understand things generally. The trouble with these models is that they give you this physics at a specific solvable point, but then you want to understand what happens when I move away from these points, when I have a more general model. And that's where this effective Dirac theory, which is much more in the spirit of field theory, becomes relevant. Right? So So what we're going to do is now try to understand this Majorana mode from the point of view of an effective Dirac model. So why Dirac model? So where does the Dirac model come from? And the reason I'm talking about this Dirac, okay, so let me first explain where the Dirac model comes from. So basically we saw that in the bulk there was a topological phase, a phase transition, a bulk gap closure. So you had so on one side of the transition you had this, and then at the transition you had this this gap closing. This is a Dirac point. And what it really means, so Dirac point generically in condensed matter, this refers to something where the dispersion is linear in K. Okay? I mean, this is broadly speaking. And the nice thing is that in any dimension higher than 0, the transition always happens, the topological phase transition always has to happen at a gap closing, like a Dirac point like this. So if you want to understand, so again, this is the spirit of field theory, if you want to understand the properties of the phases on either side of the phase transition, it's sufficient to understand what happens at the Dirac point, or near the Dirac point. Right, does that make sense? Any questions? Okay. So the Dirac Hamiltonian, so if you literally took, if you literally took the Hamiltonian we had before, this 2t cosine k minus mu tau z and all that, and went to k equals 0, but then expanded to linear order in k, the Hamiltonian just becomes this. So it becomes a Dirac Hamiltonian. But it has a mass term. This term, so at the transition point, at this crossing point, the mass term is 0, and you just have a linear Hamiltonian. And away from the point, your mass term is non-zero, and so you have to understand this massive Dirac Hamiltonian. Again, the massive Dirac Hamiltonian, you can find a spectrum. It looks qualitatively similar to that. It's E is square root of m squared plus delta minus mu squared. But this one actually allows us to understand which one is the topological phase and which one is the trivial phase, actually. So let's see why. So this comes to a rather famous. So what we're going to do is see how the 0 modes appear in this Dirac model, and that takes us to this sort of famous class of theorems for Dirac model, which are called index theorems. And the general class of these theorems say that, at least when restricted to this, they basically tell you when Dirac models of various kinds have zeros in the spectrum. And in this case, the specific one that's relevant is whenever the mass of this Dirac model changes sign, you get a 0 mode at that interface. And the mass actually, if you remember, if you go back a second, the mass was basically 2t plus mu. So basically it's telling you that whenever, 2t plus mu, and m was less than 0, minus of 2t plus mu. So m was less than 0 when mu is greater than minus 2t, and m is greater than 0 when mu is less than minus 2t. So combining this, what it tells you that whenever this combination of mu plus 2t changes sign at some point in x, you have a 0 mode. And this is a sufficiently important point that I want to elaborate, show you these, and sufficiently simple that it's nice to see how this happens. So let me just do this. So your Hamiltonian is, in this case, minus I tau y del x plus mx tau z, right? And I want to try to find a zero mode. So I want to basically solve h psi equals 0. All right? And so I plug it in. And I get minus I tau y del x psi plus mx tau z psi equals 0. I can multiply the tau y on both sides, and I get an equation which is basically this one. Del x equals mx tau x psi x. This should look like a trivial differential equation to solve. Its solution is just the exponential. And so okay. But now the tricky thing is that it's an exponential in an integral of mass. But you want the wave function to decay. Your zero mode should look something like, there's my domain wall as a function of x. My mass is changing sign, something like that. That is m of x. And I want my wave function to sort of look like this. It should be bounded. It should exponentially decay to both sides of the domain wall. So which means that this integral, this m of x, has to be less than 0 on one side and greater than 0 on the other side. And again, that's the only case when you can find a solution to this equation. If m of x has the same sign on both sides, then I'll either get something that blows up on the left side, or I'll get something that blows up on the right side. Does that make sense to everyone? So I think I have a picture of that here. Yeah, so it's the same. Yeah, so here's the same picture. One side is topological. That means the mass is less than 0. The other side is trivial. Mass is greater than 0, and I have a domain wall. And at the interface, I have a zero mode. And okay, so and this is, you can also do a solution for the Kitaev chain and find this. But the basic take-home message here is that every topological phase, because at the point I have to close a gap, at the transition point I have to close a gap, near the transition point I can understand the physics just by understanding Dirac Hamiltonians. And for that matter, in fact, one of the ways you can classify topological phases is by understanding from the classification of Dirac Hamiltonians, but that takes us in the more mathematical direction that Vijay has been going. So I'm not gonna go further into details with that. But it's one of the tools that you have to understand what the Majorana wave function looks like. Okay, and actually, also one of the nice things is if you look here again, as m goes to 0, which means as you approach the transition, this decay exponential becomes slower and slower. So this again goes back to the same point that as you approach the transition, the wave function spreads out. So you can see it directly from here. Okay. Now we go back to the question that was asked before. I sort of been telling you that one side, I told you that there's a transition, and one side is topological and the other side is trivial, and then the question is which one is which? Right? You still, clearly still, one side sign for the mass is topological and the other is trivial. It's not, but we don't know which one is which. So we have to calculate this bulk topologically invariant, and then the thing we want to show is the bulk edge correspondence, which means that in the topological phase, we want to explicitly show that there is a topological edge mode. So how do we do this? So as before, I told you that, and that was some algebra, but the bottom line that I skipped. But the bottom line is that we had used Bloch's theorem and fixing momentum to go from d equals 1, from our d equals 1 Hamiltonian to a d equals 0 Hamiltonian with particle hole symmetry. And then the topological invariant for that d equals 0 Hamiltonian is the Pfaffian that we already discussed, which was related to the fermion parity. And you can do a little bit of algebra and check that the fermion parity at k equals 0 is minus 2t minus mu, and the fermion parity at k equals pi is 2t minus mu. That was the algebra that I'm skipping here, but it's quite trivial, so you can look through it at your own on your own. Now, again, here's a spectrum, and let's see how this topological invariant changes as we vary mu. So what happens is, as we vary mu, so both Pfaffians are less than 0 still. And then when the gap closes, at this point, one of these Pfaffians change sign, so now I change into the topological phase. And then finally, as I go forward, again, okay, another so both of them are going to change sign. So as the gap closes, the Pfaffians change sign. So this suggests that the topological invariant should be a product of the two Pfaffians, because at each gap closure, one Pfaffian changes sign. So first, you get a gap closure at k equals 0. This one changes sign, and then later you get a gap closure at k equals pi. This one changes sign, and if you get two gap closures, you should be back to topological. So based on that, you can argue that this is the probable topological invariant. The trouble is we still don't know which one is trivial and which one is topological. Actually, that was a little quick, so but it was roughly okay. Any questions? So, how do we establish that there is an edge mode whenever you're corresponding to when you correspond to the bulk transition? So for this, we use this thought experiment. Okay. So what we're going to do, our Hamiltonian, our bulk Hamiltonian, was a Majorana system with periodic boundary conditions. But we want to understand what happens when we have, whether we have zero modes when we have open boundary conditions. So the way to interpolate is we have this last bond on our ring, which is this shown in green. And when this is fully closed, when this last bond is fully closed, we have periodic boundary conditions. When I set this to 0, then I have open boundary conditions. Okay? Now, what is the topological invariant? So let's say it's fully closed first, right? So it's a perfect ring. What is the topological invariant telling me about this ring? Well, remember, Pfaffian of this of the BDG Hamiltonian tells me is telling me the fermion parity of the Hamiltonian with tells me the fermion parity of the Hamiltonian with some at some k, right? And k represents the phase twist when I go around when I hop over this bond. Yeah, so let me write this down explicitly. It's important. So I have this ring, and I have this special bond, and the hopping here is t, and there is a parameter that I set that is a parameter 1 minus 2 lambda, that I can make 0, t e to the ik. That's the hopping phase going through this. And the Pfaffian of h of k is equivalent to the fermion parity with that phase twist k. Okay? So in particular, k equals 0 is the fermion parity with periodic boundary conditions. Because k equals 0 just means periodic boundary conditions. And the Pfaffian at k equals pi is anti-periodic boundary conditions. Is fermion parity at anti-periodic boundary conditions. Right? K equals, if I set k equals pi here, this becomes -1. So that's anti-periodic boundary conditions. Does that make sense? Okay. So now, remember, so now I ask, what happens if I change? So if I change, so remember, I have this T effective, this hopping, as 1 minus 2 lambda times T. When lambda goes from, let's say, lambda goes from 0 to 1, T effective goes from T to minus T. And this one is periodic boundary conditions, and this one is anti-periodic. Right? So now, if the fermion parities, so let's say my Q is equal to so let's think about the case, the interesting case, where Q is equal to -1. This means that fermion parity for periodic boundary conditions is negative of fermion parity for anti-periodic. Because Q, if you remember, was just the product of the two Pfaffians, the signs of the two Pfaffians, which means it was the product of the two fermion parities. And if this is equal to -1, means that periodic and antiperiodic boundary conditions have opposite fermion parity, which means that as I change lambda from 0 to 1, or T effective from hopping +1 to -1, my fermion parity at some point will just jump from, so I have, actually, sorry. I don't actually know about how it changes, but I know that if I look at the fermion parity at lambda equals 0, this one and the fermion parity at lambda equals 1 must have opposite signs. So as I go, at some point it'll have to flip signs. Right? So this is sort of a subtle but kind of important argument, because this is how we prove the bulk edge correspondence in this case. Any questions? No, so let's say, so if Q is equal to -1. If Q is equal to 1, then this does not happen, and you just go from, you don't flip this fermion parity, you just stay the same. So let's say we calculated it. So Q equals -1, if you go back and look at the formula, depending on mu versus T, I think if mu was greater than -2T, then Q was -1, or something like that. So if that's the case, so you can calculate Q, and if you find Q is equal to -1, then you know that the fermion parity is not changed when you change lambda. But if you remember from the D equals 0 case, the fermion parity can only switch when a level crosses 0, and actually that'll happen. You can argue, and I don't want to spend too much time on this. This happens when basically T effective is equal to 0. So the bottom line is that, based on this argument, as this hopping approaches 0, that's when you get a pair of Majoranas, but only if Q is equal to -1, because the fermion parity, because it came from the fact that the fermion parity had been changed. If Q is equal to 1, then you're not going to get this. So again, I guess we have one of these the simulations of the spectrum, and so basically what happened was, this is the spectrum as a function of lambda, and these are the bulk bands, and these are the sort of, you get a pair of modes at the interface. And as you see, this is the topological case. So they're crossing as you go from, it's just like this. As you're crossing from 0 to 1, they're crossing, and they cross at 0 energy at half lambda. And as you change mu, so what happens is, see, this crossing is still there in the entire topological region. This region is all Q equals -1. So it's still all there. And then as you get, now you go through the phase transition. Now as Q is +1, the spectrum doesn't cross anymore at 0. So your Majorana is gone. So this is sort of how this happens. Okay, good. So I think that concludes what I wanted to say about Majoranas. There is more here, but yeah, we need to go on to bigger and better things. So questions so far. So let me just summarize again quickly what I said. So far what we have learned is you can get bulk topological invariants for the Majoranas, and that you can just calculate by going to block space, take the block Hamiltonian, it now becomes a zero-dimensional Hamiltonian, and you can calculate the topological invariant. And from that topological invariant, from this bulk edge correspondence, this putting on a ring kind of argument, you can show that only when the topological invariant is -1 do there have to be Majorana modes or 0 modes at the ends. And these 0 modes are actually protected by, they're protected by the symmetry as long as you're in the topological phase. And you have to change your Hamiltonian by a finite amount to get out of the topological phase. So that's sort of the bulk boundary correspondence. The Majorana modes are these unique topological edge modes, which can only exist on the edge of a topological phase. It cannot exist by itself. And then there's the bulk edge correspondence. Right? So those were our ingredients. For questions so far? Okay, good. Sounds like you guys know everything about Majoranas. I'm skipping. I originally intended to talk a little bit about the semiconductor nanowire, which is my favorite topic, but the basic idea there is just that these Majorana chains, this Kitaev model was fairly abstract and it wasn't clear when Kitaev wrote it down what it would have to do with any real system, but it has been shown in semiconductor nanowires and topological insulators that we will talk about. These things really most likely exist in nature, and we can make them, and we can play with these Majoranas and use them for quantum computation and stuff like that. But so I'm gonna pass over that and go basically march on to the next dimension. So that is d equals 1, which will start to take you towards, I gather what you heard, what you've been hearing from Janendra, which is towards the quantum Hall state. But what I'm going to do is actually approach the quantum Hall state. Actually, I missed. So Janendra, you already talked about Laughlin argument? Okay. So you already have heard about Laughlin argument once. You can hear it twice. But I think it's going to be slightly different. And I think it's a subtle and important enough argument that it doesn't hurt to hear it twice. I promise you. Okay. So what we're going to be talking about first is a notion is a Thouless model. it's a thales, it's this notion of pumping. So this Laughlin argument is actually what's called a charge pumping argument, and it falls into this general class of what's a thales pump. So to start, so firstly, what's a pump and why? What does it have to do with topology? Well, a pump is usually you take a Hamiltonian and you change some parameter of that Hamiltonian in some way. So think of, and you should think of, and I'll show you a picture. If you take an Archimedean screw and you sort of you change the angle of that screw, you're changing the system in some way, but you're changing it in a periodic way. When you rotate by one, you're back to where you started, but you have transferred some amount of water from one end to the other. So that's your notion of a pump. So here, again, what's going to happen is we're going to have a Hamiltonian with a parameter which is periodic. And in our case, this parameter is going to turn into something like momentum. So for example, when we use Bloch's theorem, our Hamiltonian was a function of a parameter, which was k. So if we understand how the Hamiltonian varied, and this k is periodic in the case of momentum, because you have a Brillouin zone. Right? K lives in a Brillouin zone, it goes from minus pi to pi, and then the Hamiltonian comes back to itself. So you have a Hamiltonian which changes in time. So I'm going to think of the parameter as time. It changes slowly, adiabatically, right? And this should remind you of actually a famous theorem in quantum mechanics called the adiabatic theorem. And the adiabatic theorem tells you that if you start in a ground state, if you change the Hamiltonian slowly, the wave function just follows the ground state of the instantaneous Hamiltonian function. As the Hamiltonian changes, the wave function just stays in the ground state. And actually, there's a famous bit of famous topological part of this adiabatic theorem. Does someone remember? Yeah, so that's the condition. That's a good point. So yeah, there should not be any level crossing, and that's similar to this, to the gap closing that we've been talking about. So that's the condition. But there's a property that this adiabatic theorem predicts. Sorry, Berry phase. Yes, an accumulation of Berry phase. So that when you go in this path, the wave function comes back to the ground state, but up to a phase, which is this Berry phase, which is topological. Anyway, but that's an aside. It's not directly connected yet. So our quantum pump is going to be basically a similar version of this Archimedean screw. So this is what the standard standard picture of a pump is. Okay. So you take a one-dimensional Hamiltonian, which has this periodic sign potential, connected between two leads. So these are just two wells. There's two square wells, right here. There are two square wells. You have a bunch of levels here. You have a bunch of levels there, and you have this sign potential. So fine. This is standard. I mean, we can look at this potential, and then what about it? Well, what we do is we assume this potential, let's say, is very deep. It's like pretty much these barriers are infinitely high. So, okay. So then, actually, can someone say, so what do you expect in this in each of these wells? Sorry? Yeah, bound states, right? This is just like some effectively harmonic oscillator. You have some bound states. You have a ground state. You have a first excited state, and so on. Now you imagine that this potential moves. You drag this potential along. You just take the sine wave and change its phase as a function of time. So this potential just moves as a function of time. What happens is if you have an electron that is bound at the bottom as a function of time, it just moves to the right. That's basically that's the bottom line. So okay. So as a result, okay. So what would be your guess as a result of that this would do? Someone want to say? So if I had some electrons, let's say up to this energy, and I just move this potential along each period, what do you expect? So when this potential moves by one period, so that it comes back to itself, what do you expect to have happen? Yes, one electron, so one state, so each of these states moved over to the right by one, so one state would have moved from right. Okay, so that's what you expect. So that's fine. So yeah, so that's my potential. Okay. But now comes the subtlety. So that's the basic simple picture of the Thales pump. But that's sort of trivial, and I don't think it would Thales would get to put his name on it for such a trivial idea. So the subtleties are the following, but there are some subtleties. Subtlety number one is that, well, okay, you do have all these bound states in this periodic wells, but they're all exactly at the same energy, and they're actually going to overlap and form into bands. So technically, Bloch's theorem tells you that the eigenstates of these wells are actually not technically localized. I mean, you got the right answer by thinking that they're localized, but they're not quite localized. So you might worry that that this quantization is approximate, and if you make the barrier, the well, not infinitely high, it'll only be approximately quantized. You might be worried about this. But it turns out that, no, that's not true. It's actually exactly quantized. And to understand that is a little subtle, and that's what I wanted to. That's actually the detail of the Thales pump. And what I wanted to explain. So let me tell you the bottom line. The bottom line is going to be this: the pumped charge is another example of a topological invariant, and it can only change when the gap in this periodic potential, when that gap closes. That's the only case when the pumped charge can change its quantization value. So there again, it's a topological invariant, but a slightly different kind. So how does this work? Okay, so I'm just redrawing this potential here. Okay. And the key argument to do this is this notion of what's called okay. So before I go there, the reason I redrew this is the assumption that I'm going to make is that I have finite wells, so that I have a level spacing which is larger than adiabatic time, adiabatic rate. Okay. So basically, what I mean is that I'm looking at a finite system, and the system is the system is small enough so that the system is small enough so that I can so that I can apply the adiabatic theorem. The spacing between the levels is large, so that the spacing between the levels is large enough so that I can apply the adiabatic theorem. That's the assumption that I'll make. Okay, and what I'll do is I'll use this argument of what's called drawing out the pump. So the trouble was that if I have this potential like shown here, all electrons are technically delocalized on both sides of the pump. And so, so because all electrons are delocalized, I can't actually even define how many charges are on the left side and how many charges are on the right side. This is sort of a technical problem that if I want to define my pumping invariant, I want to say that I transfer some amount of charges from left to right, but the trouble is I don't know how many charges there were in the left or the right. And the way I solve that problem is by raising the potential in the middle of the pump so that it completely empties all the electrons from the middle of the pump. So if I do that, then now all my states are either on the left or on the right. Okay, so that lets me define how many electrons I have on the left and the right, and then the argument is that okay, so now I have a sequence. The sequence is I start with this potential, right? And I start with this potential, and then I dry out the pump, which is I adiabatically raise the potential in the middle so that all levels are either to the left or to the right. And that lets me count how many electrons I had on the left and the right before I start. Then I lower it back down. I'm back to this potential. I move this, I shift my potential over by one period, and then I do this again. I dry out the pump again, and now I count how many levels are to the left and how many levels are to occupied levels to the right. And the bottom line is, because I can do this counting and I always get an integer, I'm guaranteed that as long as I did not have levels on the left directly talking to levels on the right, I have a specific, an integer number of electrons. So basically, I must have an integer number of electrons when I started. I must have an integer number of electrons when I ended, and so the charge transferred must be an integer. And this basically had to do with the fact that I'm changing things adiabatically. Okay. So this is the slight, somewhat subtle pumping argument. I mean, you can think about it a little more, and maybe, I know this is a little confusing. You can think about it a little more, and you can ask me like maybe in the tutorial session in the afternoon. But the basic argument, this conclusion that this argument leads to, is that you can show that what we are arguing is that in this process of moving this potential over, the charge transport is small. Yes. Yes. Yeah, it could be any integer. No. That's a good point. But we have the adiabatic theorem, which tells us that our states at the end of one period, they all come back to the same configuration. Right? So what I'm saying is that each time, whatever integer it is, okay, so it could be some integer that I haven't really told you how to get it, but it repeats, whatever it is. That's the argument. But anyway, but yeah, this thing is I have to admit it's a little still a little subtle. But what I'm going to tell you next is actually a nice way to actually compute. How do you compute what this invariant is, right? And this is going to be something. Okay, one thing is that it's related to, one way to see it is that it's related to a Chern number. But what I'm going to tell you is a scattering matrix approach to this, which actually gives you a scattering matrix approach to the Chern number. Let me just see. Okay, sorry. So ultimately, this is going to be the answer. So let me just quickly tell you what the argument is. So how to compute the pump charge? So, and let me just tell you the answer first. The answer is going to be that I look at the reflection matrix. I have electrons in one lead, and then I have this pump. I look at the reflection matrix, or the reflection coefficients of electrons incident from the left lead into the pump, and they come back with some phase. And the argument is that the phase winding of the change of this phase as you go through the pump process is exactly the number of charges pumped. Okay, that's basically the argument. So why is that? So let me draw. I have some left lead. And then I have this is the one-dimensional pump. And let me focus on electrons. So I have electrons coming in from the left lead, and they get reflected. So I have some electrons coming in, they get reflected with some amplitude r. Okay? I'm going to assume that my energy is in the gap of the one-dimensional pump. So the Fermi energy, because if the Fermi energy is not in the gap of the one-dimensional pump, then the electrons are going to go, so I cannot pump charge because every time I pump charge, the electron will leak away through the one-dimensional pump. So I need my pump to be gapped, right? And I need my chemical potential to be at that energy. So every electron from the left lead always just gets perfectly reflected. So this tells you that this is just a phase. Okay? So there's no transmission, which means that the magnitude of the reflection should be 1. It can only pick up a phase. Is that good for everyone? Okay. But my pump Hamiltonian is changing in time, which means that this phase changes in time. Okay? And not only that, as t goes from 0 to the period, theta has to go, okay. So then the question is, what happens to theta? So theta at t must be equal to theta at 0 mod 2 pi. This e to the r, this reflection amplitude has to come back because the reflection phase is a measurable thing, so it has to come back to exactly itself. Right? So then the question is, so then the question is, if I calculate, let's say, d theta as t goes from 0 to t, what are my possible options for this quantity? Any guesses? So, actually, it's, sorry? 2n pi? Yeah, absolutely. So basically, this is just theta of t. So maybe it was too simple a question, theta of 0. And this is 2 pi times some integer. Right? So this phase winding has to be 2 pi times some integer. Okay. So now, what does this have to do with the charge pump? Well, there's a famous theorem, well, maybe not so famous. Actually, I used to avoid it like the plague when I was learning quantum mechanics, Levinson's theorem. And it's one of those I don't know. Scattering theory is always a little tricky, so it's one of those somewhat weird-looking theorems. The statement of Levinson's theorem is, if I think of this whole thing, the system to the right, including the pump and the lead, the whole thing, as a scatterer, as a scattering center, then it tells you that the number of bound states in that scattering center is related to, it's exactly related to change in the phase, scattering phase theta. So it tells you that this scattering phase theta is exactly related to, it's 2 pi times the number of bound states on basically in the scatter. So what it's telling you is that, so now with that knowing in mind, this is equal to number of bound states. Okay? Yes. Yes. Now, so the bound state, so remember I had a well on the right-hand side? The bound state, just all I know is that it lives somewhere in the pump and between the pump and the right side. In reality, we know that in the pump, it's gapped at the energy we're looking at. So there cannot be any state actually inside the pump. So basically, it's a bound state on the right side. So what happens is, no, so the theorem doesn't really tell you that. So basically what happens is in the theorem, as your parameter changes, in some sense, at some point, this bound state will go through the energy that you're looking at, and then there'll be some singularities in the scattering matrix, which creates some trouble. But ultimately, that's all accounted for in the theorem. Yes, yeah, absolutely. The length has to be sufficiently long so that the bound state doesn't decay, and that's exactly why that's exactly what leads to the quantization, because that tells you that the gap of the pump has to close to change this number. So for an infinite, if it's gapped, however small the gap is, if the wire pump is long enough, you're okay. Yes. Yeah, it's just this. It's this. No, so it has a bound state because of this guy, the right lead. Right? There are some states. So there's in the gap there is nothing here, but on the right lead there are these. So it's a well. So the pump is by itself a periodic potential, but at the end there's a reservoir. Okay. So you have this number of bound states. So the bottom line. So what this is telling you is that as you change, so it's telling you that this integer that you get is related to how the bound state changes and is related to the charge. Right? The charge pump. So ultimately it's the Levinson's theorem that lets you make the connection. Each time the potential changes from 0 to t and this phase winds by pi, the number of bound states increases by 1. And that's or occupied bound states increases by 1, and that's your pump change. Right? Sorry, you get localized states in the right lead, in that right well. But so yeah, if it's technically, so the assumption is that the length of the pump is long enough, but it's still finite, and then you have a. So okay, so the reason I talked about this is actually this is going to turn out to be a very nice way of computing a topological invariant. Firstly, we're going to show later on that this is related to a Chern number, and that's what I guess that was one of the things that Tallis did. But oftentimes it's going to turn out that this is easier to compute numerically. Computing this phase shift is easier than computing the Chern number. Okay. All right. So I think, yeah, I think that's about as much as I'm going to say. You can play with, so this is some simulation of the band structure, yeah, of the band structure of the system, and how much charge is, so, and calculating this, this invariant, but now instead of doing it over the entire period in time, you can ask how it varies in time, and depending on the band structure, depending on your chemical potential, so at perfectly quantified limits. Okay. So okay. So that ends my discussion of the non-topological of the just pure charge pumping. Questions about that? Okay, so now we're ready to see Laughlin again. Okay, so Janendra already, so the Laughlin, the setting for the Laughlin thought experiment is the Hall effect. And Janendra already told you about it a little bit, but let me just show you the picture and quickly, just to refresh your minds. So the system is you have a two-dimensional electron gas in a magnetic field, and this is really just a classical Hall bar at this point. You're applying this is a so-called four-terminal measurement. You're applying a Hall voltage current from this left lead to the right lead across the system like that, and you're measuring a voltage that you're measuring a Hall voltage between 2 and 4, and you can also measure a longitudinal voltage between 1 and 2. So the Hall voltage is perpendicular to the current that you're driving. The longitudinal voltage is along the current that you have. And then the current and the electric field that you can turn the voltage into an electric field and the current into a current density, and there are some conductivities that you can define, which are longitudinal and Hall conductivities. And okay, this sort of tells you how to measure all of these things, but I'm not going to go through it. But I should just tell you that it's a little bit, these things are a little bit subtle. For example, like, yeah, the Hall conductance, once you measure those electric fields, the Hall conductances and the currents, it's not actually quite that completely straightforward relation. You get this, okay, you're starting with a complicated relation a simple relation, which is that current is just linear, is proportional to the electric field. But the trouble is that in any configuration, if you're not careful, you will have both longitudinal and transverse electric fields, and you have to account for all of that. And really the constraint in the system, you have both longitudinal and transverse electric fields, but you don't have any transverse current. The current is entirely longitudinal, and so when you account for all those things, you get a somewhat complicated relation. But this was something that Janendra mentioned yesterday. If you want to understand what the Hall conductance is for a perfect clean system, whether it's classical or quantum mechanical, you can always go to a frame where if you have both electric and magnetic fields, you can go to a frame where you get rid of the electric field just by boosting the velocity. And in that frame, you don't expect any current. So then when you come back to when you transform back, your current is just proportional to the density times the velocity, which by itself gives you a Hall conductance. And the Hall conductance that you get, and this is sort of constrained by Galilean invariance, so-called, and Galilean invariance is just the fact that you can just boost, you can just change your velocity. Just this fact, it tells you that Hall conductance is proportional to density, divided by the magnetic field. And as Janendra introduced, the density divided by the magnetic field is the filling fraction, so Hall conductance should be related to filling fraction. The filling fraction is basically defined as the number of electrons per flux quantum in your system. But something funny happens, which is that in solid-state systems, which is that you have some amount of disorder, and as soon as you have infinitesimal amount of disorder, basically, okay, so the mechanism for this Galilean invariant Hall conductance is that basically when you have a magnetic field, as you heard from Janendra, all your electrons are bound into Landau levels and they're going around in circles. But in a magnetic field, they're all going around in circles. Now, if you apply an electric field to this whole thing, to the system, the whole gas just starts sliding down. right? And that's what gives you a conductance, which is proportional to the density, and that's the end of the story. But if you have even a few impurities, then basically that pins this whole gas from moving. Most of these electrons in synchrotron orbits, they just get stuck. And you just have ultimately what are going to turn into edge states. There are only a few states that can move, and you get quantized conductance. That's going to be the story. And because of that, as Janendra mentioned yesterday, if you look at the Hall conductance or Hall resistance shown in red, it's perfectly quantized, and it's so quantized that it is turning it has turned into a standard for the mass. So before we used to have a kilogram, which was just sitting in I guess it was sitting in France, and in all our national labs, you would have 1 kilogram, and people would worry about, oh, did like a virus land on it and change how many mangoes we get per rupee. But okay, but we don't have to worry about that. We can now use a quantum Hall system to calibrate that. Okay, so now, so why? And this was a question that I guess this was the question the Laughlin pumping argument answered, is that why is this Hall conductance so perfectly quantized? I mean, even in the presence of disorder, interactions, all kinds of things. What is it? What is it about? So to see that, let's imagine that you put, and again, you've seen this before, but I'm going to put it in this context of the Thales pump now. You just take your 2-dimensional electron gas and put it in an annulus, and somehow this got renamed the Corbino disk in this context. And now what you do is, and this is basically the Arnav-Bohm type experiment. You apply a magnetic flux right to the center of this annulus, right? And you increase this flux by some amount, by a flux quantum, or a few flux quanta slowly as a function. Now, every time your flux changes by a flux quantum, so what do you think happens that connects it to the Thales pump? Someone want to say? We already, from the Arnav-Bohm effect, do you remember? Yes, perfect. So every flux quantum, the Hamiltonian returns to exactly where you started. Because if you have a whole flux quantum, so the if I think of the Hamiltonian of the electrons in this ring, I can introduce this. I can choose a gauge where the vector potential is only non-zero on just this one line along this disk. And I have a hop. So if I think in terms of a lattice model phase, I have a hopping across this. When the electrons go across this region, they hop by an integral I a dot dl in this little edge, which is basically e to the I flux over flux. When I put my h's and e's and c's in there, okay? So the Hamiltonian comes exactly back to where I started. So what that tells me is now going from left to right. So what that tells me, based on this Thales pump argument, every time this Hamiltonian, so I think of this as a one-dimensional system along the perpendicular direction. I think of the inner ring as one of my left lead, and I think of the outer ring as my right lead. And what this is telling me is that when my Hamiltonian is completely gapped, I can only transfer an integer number of charges from the inner lead loop to the outer. It could be 0, and I have to argue why it's not 0, but it tells me that it has to be an integer. Right? Yep. I have 4 minutes. Yes, thanks. Now, so that's the basic, and that's the basic argument for Laughlin. Now, okay, you might ask intuitively, and I guess this you've already seen before from Jayendra, why should there be any current in the first place? Well, it's because when you change the flux as a function of time, that's changing the vector potential as a function of time. And when you change the vector potential as a function of time, you basically generate an E. That's basically the Faraday's electromotive force, because you have a flux that's changing as a function of time. You have to generate an electric field as a function of time that goes around, that points circumferential along the disk. And if the system has a Hall conductance, then that should be equivalent to a current that should drive a current perpendicular to the disk. So what that tells you, okay, so you should get an electric field that should give you a current, and what that tells you is, and the current, the Hall conductance should just be the current divided by the rate of change of flux. And now we're almost ready to argue why things are quantized, because if you now think of one cycle of this flux, the flux changed by one flux quantum. The charge that was pumped was the current times delta T. Current, we just argued, was Hall conductance times d phi dt, which was the electric field. So now d phi dt times delta T is delta phi, and delta phi is h over E. So what it tells me, finally, is that the charge pump is Hall conductance times h over E, which means, but this is an integer. So really powerful, the beauty of the Laughlin argument is that it tells you that you have any two-dimensional system, doesn't matter. If you have, it could be interacting, not interacting, even that's not relevant, but the Hall conductance has to exactly be an integer times and in fact, at this point, you should be sufficiently worried about this argument that how do we even see a fractional quantum Hall effect in that case? And it turns out that this argument itself tells you, and this is again a typical kind of argument in this matter, which is that there was an assumption that you had well-defined nice ground state and one of them. So it tells you that, okay, if you get something which is not an integer here, there has to be something funny about the ground state, like it has to be degenerate or something like that. It can't be a simple non-degenerate ground state. Right? And this is the kind of arguments that go over, let's say, to Leaf-Schultz-Mattis theorem and so on. Okay, so and the rest of this discussion was the Laughlin, talking about Landau levels, which you've already seen from. So you can understand this argument in terms of Landau levels in general, but okay. So that concludes what I wanted to say about the Laughlin pumping argument. So the bottom line is that there is this so given a one-dimensional system with the periodic Hamiltonian, you can define a charge pumped, which is just how the scattering matrix, scattering phase shifts as a function of time over one period, how it winds. And you can view a gapped one-dimensional system, that's the Laughlin argument, as, a gapped two-dimensional system in a cylinder or annulus geometry, the 1D system, apply this argument and argue that Hall conductance must be quantized. So so I think that'll be it. So the next, what I'll do, just to give you a quick sense. So the next thing that I'll talk about is basically how this quantized Hall conductance must also imply the existence of edge states, just from the story. All right, thanks. So, question? Yeah. No, yeah. So you want to make sure that if your whole system is starts to slide, I think it breaks some of the adiabatic arguments that the system is gapless. I think that's the. So intuitively, at least, you do not want the situation where you don't want you want contribution of sort of electrons that are moving along and giving you conductance. You don't want the whole gas sliding. You want to basically anchor or hold down this gas.
What I wanted to ask is, yesterday what we saw in quantum Hall effect, we had this annulus, and the flux actually pierced through the annulus, right? Like, but here in your case, it's as if like you have a solenoid which doesn't go through the bulk of the material.
Yeah. So no, you technically no, you. So I think the catch is how big you want this hole that I have. I drew it big, and for my Thouless pumping argument, I kind of want it to be big so that I have a reasonably sized reservoir. But because what I don't, what I want it to be big enough so that okay, but at some level it doesn't really matter if it.
Because if the flux doesn't go through the material, then it's not a gapped system at all. It's not a quantum Hall system, right? So
no. Sorry, no. Let me clarify that. This flux was not the magnetic field. So on top of the flux that I was applying in the hole, there is a fixed magnetic field everywhere in that part. So this flux is not part of that flux, right? Yeah. Okay.
When there is a mobility gap.
Actually, no. So that's a great question, but I don't know. But I can answer it just to you probably. But so the thing that I needed was that the reflection is unitary from the left. So which means that the modulus of this is 1. Nothing gets transmitted into the pump. But that's exactly the condition that there is no transmission in the 1D pump. So it's actually that there is a mobility gap. I don't actually care that there is a spectral gap. It's that the transmission, so an electron that comes in from the left gets reflected, and in theory, something should get transmitted. And I want to avoid just that. That's the quantity that I want to exactly avoid. So it's exactly the requirement that I have a mobility gap. So this is, I mean, from practical, just for the students, from a practical point of view, that's actually, so I've been talking in terms of clean systems and assuming that there are no sort of states in this 1D pump. But that's actually not, for the scattering argument to apply, that's not the criterion at all. I just want to make sure that nothing moves, no electrons are transmitted along this, which means that any disordered localized system, any disordered system which has states everywhere, actually, as long as they're not delocalized, it doesn't matter. Which gives the real criterion for the quantization of the Hall conductance is that there are no delocalized states in the middle in the bulk of the material. Everything is localized, and so there's no longitudinal. Yeah, there's no longitudinal transfer. Yeah. So actually, so no. So in that context. Yeah, in that context, I think it's actually that argument is still a little bit hand wavy in my mind to me. So I think the connection there is a little less rigorous. But yeah, yeah. In fact, no. So the drying out of the pump should work actually, but it doesn't require disorder. Yeah, that also works whether you have disorder or not. That's correct, because you're just using it to localize electrons on one side or the other. But what I was just saying, that the fact that you don't have conductance, that's the real criterion, is completely actually enforced by, I mean, it's completely transparent by the fact that this is one and not some fraction. No, because the adiabaticity assumption. So all I have to do in that case is to make sure that I'm adiabatic relative to the typical level spacing in my localized space. So I think that is also one. Because okay, you have to, yeah, it's a little more subtle. I agree, but there you have to. I mean, you have like this Poisson level spacing for states that are nearby. But then as you, as I guess, so then what you have to think about is that but then there are going to be levels that are closer and closer, but they're going to be further and further away. So there is some balancing of the exponential matrix element and how close. So you're going to get levels that are close by in energy, but they're also going to have exponentially small matrix elements. But I think it still works.
Let's thank Jaydeep once more. And we break for tea and coffee now and gather back